Good morning. Integers can be represented using any integer greater than 1 as a base. Although we commonly use decimal base 10 representation, binary base 2, octal base 8, and hexadecimal base 16 representations are often used, especially in computer science. Given a base b and an integer n, we will show how to construct the base b representation of this integer. We will also explain how to quickly convert between binary and octal and between binary and hexadecimal notations. Representation of integers. Let b be a positive integer greater than 1. Then if n is a positive integer, it can be expressed uniquely in the form n is equal to a subscript k, b to the k, plus a subscript k minus 1, b to the k minus 1, plus dot 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 dot, plus a subscript 1b plus a sub 0, where k is a non-negative integer. A sub 0 through a sub k are non-negative integers less than b, and a sub k is not equal to 0. Remark. Theorem 1 is employing formal mathematical terminology to express that our number system is a positional number system. For example, 954 means 954 base 10 and can be expressed as 9 times 10 squared plus 5 times 10 to the 1 power plus 4 times 10 to the 0 power. The digits of the number 954 are in positions 2, 1, and 0 respectively. Furthermore, the positions are exponents of the base. Convert an integer in a foreign base to decimal. Example 1.1. Find the decimal equivalent of 10101 quadruple 1 base 2. What I'm going to do is I'm going to make a table, and I'm going to have 5 columns. In the leftmost column labeled position, I'm going to put the positions starting with the top row and moving 8 down to 0. Then I'm going to put the corresponding digits that are in those positions in the next column and the equivalent decimal value in the next column. And then I'm going to exponentiate the base starting in the bottom row. 2 to the 0 is 1, 2 to the 2, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. Finally, 2 to the 8 is 256. Then I'm going to multiply the decimal value of the digit times the exponentiated base to get the value of that digit in its position. So I add all those up, and the decimal equivalent is 351. Example 1.2. Find the decimal equivalent of 10101 quadruple 1 2 by means of converting the binary value to hexadecimal value before converting it to decimal value. The secret here is every group of 4 bits, called a nibble, can be directly converted to a hexadecimal value. So what I'm going to do is group the binary representation as 10101 quadruple 1. And then what I'm going to do is I'm going to convert every nibble to its hexadecimal equivalent. So looks like I got a little out of whack here. And but in any event, what I have is 10101 and quadruple 1 base 2 is 15F base 16, and now I can convert the hexadecimal value to decimal quite easily. I only have 3 positions and 3 digits. Of course, F translates to 15, and so I multiply this out and get 351, the same as I did before. Example 2, what is the decimal expansion of a number with octal expansion 7016? Using the same kind of table before, I come up with 3598. Example 3, what is the decimal equivalent of 2AE0B, 2 alpha EZ0 Baker base 16, and using the same kind of technique before, I come out with 175,627. So here is an algorithm to convert a decimal integer in equivalent value in a foreign base conversion. Create a table having 5 columns labeled divisor, dividend, quotient, remainder, and foreign digit. In this algorithm, we're doing the reverse of what we did before. Before, what we did is we took a value in a foreign base and converted it to decimal. Now what we're going to do is we're going to take a value in decimal and convert it to a foreign base. Start with the top row. In the column labeled dividend, put the decimal integer value to be converted. In the leftmost column labeled divisor, put the foreign base radix. If the value in the dividend is 0, stop. In the column labeled quotient, put the integer quotient of the dividend and the divisor in the columns to the left. In the column labeled remainder, compute the remainder of the dividend divided by the divisor. In the column labeled foreign digit, convert the remainder to a single digit in a foreign base. 2.7, place the value of the quotient in this row in the column labeled dividend in the next lower row. 2.8, go to step 2.2 above and repeat the process from step 2.2 to this step. 3, print the value in the foreign base starting with the most significant digit found in the bottom row of the table that is not 0 in the column labeled foreign digit. Print the subsequent digits from the foreign digit column, moving from the bottom row to the top row. So here's an example. Find the octal equivalent of 1, 2, 3, 4, 5 deal. So my divisor is the foreign base that I wish to go to. My initial dividend is the decimal value. So what I do is I compute the quotient of 1, 2, 3, 4, 5 divided by 8, and its remainder 1. And then it's the foreign digit is a 1. Then I copy the 1545 down to the next row and put it in the dividend column, and I perform the next division. 192 is the integer quotient of 1543 divided by 8, and the remainder is 7. The foreign digit is 7. I copy 192 down to the dividend column and divide by 8 again, and I get 24 and a remainder of 0. I copy the 24 down and get a quotient of 3 and a remainder 0. And now this part is very important. Copy the 3 down, even though we know that it isn't divisible by 8. And we nonetheless divide 3 by 8, getting a remainder of 3. So what we're going to end up having is 4 digits, and they are 30071, moving from the bottom to the top. Find the hexadecimal equivalent of 17730. So we used the same technique before, dividing our initial decimal value of 17730 by 16, getting 11070, and our remainder of 10, and successive quotients of 691, 43, 2, and 0, and successive remainders of 14, 3, 11, and 2. Now, of course, the conversion to the foreign digit is not trivial. 10 goes to A, 14 goes to E, 3 goes to 3, and 11 goes to B, and 2 goes to 2. And so our equivalent hexadecimal value is 2 Baker, 3 easy A, alpha. Example 6.1. Find the binary equivalent of 241 base 10. Well, we could just divide by 2 successively until we get quadruple 10001 as shown. Or what we could do is we could do this more quickly by converting it to hexadecimal first, and then converting the hexadecimal to binary. So converting it to hexadecimal, we get a value of F1, and then what we know is by the table that we store in our head is F goes to quadruple 1 and 1 goes to quadruple 001, and so this way makes fewer mistakes. So our first algorithm 1 is constructing base B expansions modified to cover decimal integer values from foreign base B, where 2 is less than or equal to B, less than or equal to 36. So instead of what we have given in the books, I've given you a tested algorithm that's in C++. It returns a string, and string is not a reserved word, so I better italicize that. And the name of the routine is 2FB, which stands for 2 foreign base. I'm given a dividend and a divisor. This is the initial decimal value, and this is the foreign radix. I begin with an empty string, and then I have something to convert my remainders, which are integer values, into single characters. And so I've got this array that I've represented as a string that runs from 0 to 9 and then from A to Z. While the dividend is greater than 0, I compute the quotient and remainder, and then I use the remainder as an index into this string here, so that a remainder of 0 gets me character 0, a remainder of 10 gets me an A, a remainder of F gives, a remainder of 15 gives me F. And then what I'm going to do is I'm going to prefix it onto the existing string, this character. That way I'm producing them in reversed order, and then finally what I do is I make the old quotient the new dividend, and I continue this until the dividend is no longer greater than 0, it's equal to 0, and then I return that value. Example 7.1, convert 11, 1110, 1011, and 1100 to octal base 8. Well, here what we're going to do is, starting with the least significant bit, form groups of 3 bits, octets, moving from right to left. Fill the most significant bits of the last octet with zeros. So our binary number I've reformatted into 011, 111, 010, 111, and 100. Convert each octet to its corresponding octal digit. Octal digits can be computed by finding the decimal value of the octet. So the most significant digit, 011, is just a 3. 111 is 7. 010 is a 2. 111 is a 7, and 100 is a 4. So that was fast. Now convert 11, 1110, 1011, 1100 to hexadecimal base 16. Again, starting with the least significant bit, form groups of 4 bits called nibbles, moving from left to right. Fill in the most significant bits of the last nibble with zeros. So you can see that it's the same as before. The only difference is the most significant nibble has got 0011 instead of being a truncated just 11. Convert each nibble to its corresponding hexadecimal digit. 0011 is a 3. 1110 is an E, as in easy. 1011 as a B, as in Baker, and 1100 is a C, as in Charlie. Convert 765 octal to base 2. Solution: replace each octal digit with its binary equivalent, a group of 3 bits called an octet. So 7 is 111, 6 is 110, and 5 is 101. Remove any leading zeros, and in this case there are none. And example 7.4, convert alpha 8 dog, A8D, base 16 to base 2. Replace each hexadecimal digit with its binary equivalent, a group of 4 bits called a nibble. So A is 1010, 8 is 1000, and D is 1101. Remove leading zeros, and in this case there are none. So here we have some, I think we'll stop there and continue.